Hi everyone, my name is Bill Yuchen Lin. I'm a final year PhD student at USC, advised by Sanh. And Kangmin is a master student at USC. Chris is an incoming PhD student of our lab. And Beiwen was a summer intern at our lab from Tsinghua University. And we are going to introduce our work on unsupervised cross-task generalization via retrieval augmentation. So recent studies shows that it's very promising to train a massively multitask NLP model based on transformer language models. So the general recipe for training such a model is to first create a mixture dataset of various diverse upstream tasks which share the unified sequence-to-sequence format. For example, task I is a sentiment analysis task, and this task TJ is a summarization task, and both of them now are in the sequence-to-sequence format. So we use this combined dataset to fine-tune a pre-trained sequence-to-sequence language model such as BART or T5, so that the trained model can be very powerful in all these upstream tasks. Beyond multitasking, a particular benefit of such massive multitask model is that the cross-task generalization ability. Let's look at some concrete examples. The CrossFit framework fine-tunes a BART model on 160 diverse NLP tasks, and then when we need to train it for a new task, an unseen task, we can use only a few annotated examples for fine-tuning the upstream model in order to generalize to this new task. So this is a few-shot learning setup, and we have to assume that there are human annotations. It's very necessary for using these annotations for generalization. So therefore, the applications of CrossFit models would be very limited. Later, a Google team proposed FLAN, and a Hugging Face-based team proposed T0. Both of them use natural language templates to unify the datasets of the very diverse NLP tasks, such that the produced multitask model is more promising in zero-shot task generalization. So in our paper, we focus on improving the models, the generalization ability of the models like T0. So let's formulate the problem of unsupervised cross-task generalization here. So given a multitask NLP model, we want to make this model to perform a new task, which is never seen before. We consider a situation where we have a few unlabeled examples, where we call them as query examples. So in this unseen task UI here, we have a set of unlabeled query examples QI here. So for these query examples, we only have their input text of them, but not the outputs at all. And we want to update the upstream model so that it can generalize to this new task. Therefore, it's a zero-shot setup for task generalization, and it's more general in terms of the number of the unlabeled data for the target task. And in this paper, we want to focus on how to augment such a multitask model by using these query examples to retrieve some additional data that shares relevant skills for relearning the model to generalize across tasks. So from this motivating example, we can see that these two retrieved tasks are the most relevant skills for this unseen task, and we want to use the data from these two retrieved datasets to fine-tune the model so that it can generalize to this new task. So in order to benefit from such retrieval augmentation, we propose a novel framework named ReCross. ReCross has two ranking stages. In the first ranking stage, we use an encoder to encode each query example and then query the initial candidates from the pre-computed dense index of all upstream data. So this process is done by a maximum inner product search, which is extremely efficient. And then given these initial candidates R prime here, we use a more powerful re-ranker module that takes each pair of the query example and the candidate example for further justify further justify the suitability of this pair to use a certain candidate as the final result. So we use the re-ranker here to give a score for each pair of the candidate and the query, so we can take the subset of the candidates that are ranked at the top for fine-tuning the upstream model so that we can generalize towards the target task. Specifically, to compute such a dense index, we reuse the encoder layers of the upstream model. Recall that the upstream model is an encoder-decoder structure, so we use the hidden states between the encoder and decoders to build a dense vector representation for all the examples in the upstream data. The dense vectors then form a dense index here, which will support the MIPS queries in the future. We also propose an algorithm to generate distance supervision for training such a re-ranker. The re-ranker here is a cross-attention encoder, and we use a reward base in practice. The main motivation of the proposed algorithm here is to is to use the results from the dense retriever and then run multiple rounds of the virtual learning such that we can estimate the utility scores of the candidates by looking their loss. We leave more detailed description in our paper, so please refer to our paper for the implementation. And for our evaluation, we choose 10 target tasks that are unseen in the upstream data, and we use our own BART0 as the base language model, which is comparable to T0, but is much smaller. Considering the computation cost for evaluating at scale, we use a BART0 instead of T03B as the base model. Then our first baseline method is to use a random retrieval here. For this kind of retrieval augmentation methods, we run 5 times and five rounds of experiments, and each round has a different query set. And so we can have a more comprehensive understanding of the performance of this retrieval augmentation. So we have a mean, median, mean, and max on these 4 dimensions to validate the effectiveness of this retrieval augmentation framework. And the random baseline is not as very surprising because we expected the random retrieval will not improve the overall performance, and it is indeed the case. And when we are using sentence BERT is like using semantic similarity as the criteria for retrieving relevant skills or relevant examples for fine-tuning the model. And we found that if we look at the maximum of the SBERT results, we can see it's improved. It outperforms the Verena BART0, but on the median or the mean, it's not very significant. So we can it's also expected because we think like the semantic similarity doesn't necessarily mean like these retrieved examples should be beneficial for generalization. And we can see here ReCross prime, and ReCross prime here is like our method but without the re-ranking, so there is no re-ranker here. And we can see like if we use we reuse the BART0's encoder as a example encoder to build the index, we found that it's much more beneficial, and it improves the results on all 4 dimensions, the mean and median. And if we look at the maximum performance of the ReCross index is like improved by 4 points. And also this is our full version of our ReCross project, and we can see the performance is further improved by 1 point on average, and also it's about like 5 points comparing to the BART0 on the maximum dimension. And this is the delta between ReCross and the Verena BART0. So we can see that the performance is much improved if we use ReCross for doing the retrieval and then generalize the model to the target tasks. And we also have some additional analysis in our paper, like using big bench datasets, which are more challenging, and also using different hyperparameters here, like more configurations of our experiments, like using different query size, under different query size, and using different retrieval size, and also the upsampling ratio. So all these analyses are included in our paper. Please refer to our paper if you are interested in this. And to better understand the retrievers, we also draw a heat map to visualize the distribution of the retrieved data for each target task over all the upstream tasks. We can see that the behavior between SBERT and ReCross, the behavior is very different from each other. And we think it's very important future direction to get a deeper analysis on the task correlation and also the example utility from the retrieval stage. So as a conclusion here, we would like to argue that ReCross is a retrieval augmentation method for unsupervised cross-task generalization. It has 2 ranking stages, and it's very simple, straightforward, and very intuitive. And it results in like a very significant improvement over non-retrieval and even some retrieval-based baseline methods. And our future directions include like we want to have a more rigorous task representation for indexing, and maybe also some parameter efficient tuning for fast adaptation. So we can see that the relearning process is very important in our retrieval augmentation framework. And right now we only use like 2 epochs of just normal like SGD or ADAM to do that. But we want to see if we can use some new methods to use unlabelled data here as well to get the relearning process. Okay, that's all. Thank you very much.